tell us about this super axion gas and their predictions.
All right. Thanks a lot for the invitation and nice introduction. So today I'm going to present you the work I've been doing with Lawrence and Francesco, who is now a postdoc at UC Santa Cruz. So when I give a talk, I always like to start with something interesting about what happened today in history. And then, for example, I gave a talk on the birthday of Max Planck before, and another talk on the day Ernest Lawrence earned the Nobel Prize. And I did a little search today, and then I found out that today is the most boring day in history. And the reason was that people wrote the program and they searched for the keywords of what happened on each day in the past century, and they found out that nothing really happened today, 62 years ago. All right, so here's the talk. So first of all, I'm going to review with you some strong theory problem and what we exactly mean by SaxiGUTs, and we will review the axion misalignment angle. And here is the saxion dilution. So I will talk about the key idea in our project. And eventually, I'll give you a list of the experimental predictions that we have from SaxiGUTs. So first of all, strong theory problem. We know that we always have this GG dual, the gluon coupling. That's all allowed by all of the symmetries. And this theta bar is the dimensionless coupling. However, what we know is that from experiments, the neutron electric dipole moment translates into a theta bar less than 10 to the negative 10. So the question is that why is this dimensionless coupling not of order 1, but so tiny? So the most promising solution is the Purchey-Quinn mechanism, where we just promote the field theta bar to the parameter to a field A. A is the axion. Fa is the axion decay constant. So by solving the potential, you will see that the minimum of the potential will happen when the field axion exactly cancels the dimensionless coupling. So this is why we don't see a theta bar parameter in the Lagrangian. And here's what we really mean by SaxiGUTs. So it is a class of theories where we have the supersymmetric grand unified theories, and we have the Purchey-Quinn symmetry, which is the usual QCD axions. And the key feature of our theories is that we have a simultaneous breaking between of GUT scale and PQ scale. So what it means is that we will have to have PQ scale and the GUT scale, the SU5 unification scale, to be of the same order. So in this talk, we will take it around 2 times 10 to the 16 Jeff. And we have found in the literature that we have a few examples of SaxiGUTs. Those are what we found, so there are not very many theories about this. And I will explain it in a minute why people didn't have a big interest about this. The reason was axion misalignment mechanism. This is the mechanism to produce dark matter axion. So if we imagine that we have the temperature below the PQ scale, which means that PQ symmetry is broken, so you will have a set of fields that break PQ with the VI and with the PQ charge QI. A is the axion supermultiplet, which consists of the saxion, axion, and axion. And VPQ is the PQ scale. It has to be defined this way, QI squared, VI squared, so that all these SA and A total fields are canonically normalized. And because we're talking about the flight direction in the potential, so A would have been massless after P2 breaking. But when the temperature drops below the SUSY breaking, then the SUSY breaking contribution to this saxion mass turns on. But then axion still stays massless around the bottom of the potential. But what happens after the temperature drops below the QCD scale is that the anomaly effect turns on, which means that axion becomes massive now. And here, the way we relate the PQ scale and the decay constant of axion is by the so-called domain wall problem. You can calculate the domain wall number for a given theory. And this domain wall number also tells you the number of vacua along the minimum of the potential. So if we just look at this direction, the axion direction, what happens is that initially you have a flat prior, so axion can take on any field value. But when the potential of axion turns on, then you may not be so lucky that you're at the true minimum. You could be off the true minimum, and that's the angle we're talking about here is the misalignment angle. So the bigger the misalignment angle means that you have a bigger potential energy to begin with, and that will contribute to the axion dark matter. As you can see that when the temperature slowly drops below QCD, then the anomaly effect turns on slowly, which means that the mass of the axion was initially massless, and it turns on as a power law, and after QCD phase transition, then it becomes a constant. That's what we know about the axion mass. Alright, so how do we calculate it? So we will look at the axion equation motion. Here H is the Hubble constant, Ma is the axion mass. And rho A is the axion density, which consists of the kinetic term and potential term. And that's why we're saying that if you start with a big misalignment angle, then you have a big potential to begin with. And that would translate into a dark matter balance of 0.11, which is the observed volume, if Fa is not too much bigger than around 10 to the 11 GeV. You can always make Fa bigger by fine-tuning the misalignment angle. You can always do that. But the thing is that it is unnatural. There's no reason why the misalignment angle has to begin with 0 when you turn on the QCD anomaly. So this is the reason why people lost interest in SaxiGUTs. They don't think of PQ and gut scale to be of the same order because axion misalignment mechanism was discovered in 1983, and people realized that Fa has to be far below the gut scale. So that's why people lost interest in this kind of class of theories. But now I'm going to tell you how we don't have to do much work, we don't have to introduce new physics, new particles to solve this problem. We can actually put the PQ scale back to the gut scale. So they could be of the same origin again. So here's how we do it. We use the saxion cosmology. And let me explain why we care about saxion. So first of all, in our theories, we are assuming that saxion energy density would dominate the total energy density of the universe, which means that we need to know the exact energy evolution of the saxion to solve the equation motion for the axion. The second reason is that saxion will eventually decay, and you produce a lot of entropy. The way people calculate dark matter balance today is to look at the ratio of dark matter energy density to the entropy density. So if you produce a lot of entropy, which means that you're effectively diluting dark matter. And that's what we have to do to dilute the dark matter from axion so that we can push up the Fa. So how do we calculate saxion cosmology? First of all, you will have the same equation motion as the axion. So this phi s is the saxion field and ms is the mass of the saxion. And what happens is that initially inflation could set the minimum of the saxion from some minimum, which is not the true minimum today. So this is, again, displaced from the minimum. So initially it's stopped at that field volume because the Hubble friction term is much bigger than the mass. But when H drops below ms, then it starts to oscillate, meaning that we're getting the condensates of the saxion, and so saxion energy density just scales like matter. It's just the usual matter evolution. And eventually, saxions will decay when Hubble rate is around the decay rate of the saxion. So here's the summary of the matter-dominated universe. We start with some radiation domination. Here, rho m is the saxion energy density, which is the matter energy density. Rho r is the radiation. Because it scales slower, it drops slower for matter, so eventually at some point, saxion can dominate over radiation. So we now enter some era of matter-dominated phase. But this MD era itself consists of two different phases. The first one is adiabatic, the second one is non-adiabatic. The difference is that in this era, the decay of the saxion is not very effective yet. So we don't have a lot of relativistic decay products from the saxion. But when you enter this region, then the relativistic decay products of the saxion starts to dominate the original existing radiation, which means that you're producing more radiation from the saxion decay than you had in the beginning. In other words, it is saying that we're actually reheating the universe. We're generating a lot of entropy, we're reheating the universe. So this happens in MDNA era. And eventually, saxion will decay. and giving all of his energy back to radiation again. So what we found out in the analysis is that we said that axion is going to start oscillating. So where does it start to oscillate? And it turns out that if we look at this plot, this TNA is the temperature where we entered this MDNA era. This is the blue band. And this yellow band is telling you the oscillation temperature of the axion. And for the reheat temperature of our interest, you can see that TNA is always higher than the temperature when axion starts to oscillate, which means that axion always starts to oscillate in this MDNA era. And then we don't look at reheat temperature lower than 3 MeV because that's excluded by BBM.
Could you just say a little bit more about what is it that's defining this non-adiabatic era? Because usually, right, when the decay starts to become important, you would think that the matter, you wouldn't have matter domination anymore rather quickly. But you're saying there's a reasonably sized, there's a reasonable range of temperatures, say, where somehow the matter, the oscillations are still dominating the expansion, and yet the decays are important. Could you explain more what defines that era? What is exactly important there?
Yeah, so what is important here is that, so first of all, we have to assume that the reheat temperature is low, which means that the saxion will decay late. And what happens is that here, for the whole process, you can imagine that the saxion is decaying. But then the decay products may have energy density lower than the original existing radiation. So this is the initial
But they're just
radiation.
dominating the radiation part, which
Exactly.
is subdominant.
Yeah, which is still subdominant to your matter. But then now, because you're producing more radiation than what you had before, that means you're reheating, you're generating a lot of entropy.
So, but naively, you would think that, I would think naively that that's all fine, okay. But then when the matter, the oscillations in this case, finally decay, what happens there completely overwhelms that produces most of the radiation, because that's where most of the mass is, most of the energy, I guess is the right thing, is converted to radiation. So why is it important that the radiation is getting some correction there?
Yeah, so the big difference is that if you look at Cobb-Turner, then you would see that most of people would just do a Southern approximation where they assume that there is no production of radiation from the saxion decay. And all of a sudden at T reheat, then all of the energy is converted to rho R. So you would expect that the line looks at that, it follows this usually, but all of a sudden you have a jump in rho R.
Right.
Yeah, but that's just a Southern approximation. What I'm showing you here is actually the full numerical evolution of the universe. So we do have an era where the decay products are already higher than the original rho R. And then, and not most of the energy will be given here. It's actually kind of distributed in this era. But yeah, this is probably not Johnson scale. If you look at the, this is Johnson scale, but it's not for temperature. If you look at this temperature, and this temperature, the ratio of, so in log scale, this length will be 1 to 4. So that era is actually kind of short. So it's only 1/5 of the total era in log scale. So that is just the late stage of matter-dominated era.
Does it matter very much? Is the sudden approximation really that bad?
So it depends. So if you produce, for example, axion or any dark matter in this era, then the sudden approximation is not bad at all, because you're just kind of suppressing this MDNA era into a point.
Right.
But what would be bad is that if axion or any dark matter mechanism is produced here, which means that you're actually right in the middle of the entropy production. So if axion is produced here, it doesn't get diluted by this amount of entropy. It gets diluted by the entropy produced after axion is already generated. So it depends. So if you generate dark matter here, then Southern approximation is fine. But if you generate dark matter here, then the Southern approximation will not work well. And it's actually pretty bad, depending on where you are. Yeah, so, but what we found is that in our classical models, axion oscillation temperature is always in this MDNA. So you only receive entropy production after it is oscillating. So then we have to do a full numerical calculation. But I will also show you the analytic way to do it if some dark matter is produced in this era.
So that energy scale, the end of the red band is where on this other plot?
Sorry.
So you have the red band
Yeah.
ends at, I can't read
Oh, it's 1
3 or
MeV
4.
to 3 MeV.
Right, and where is that on this plot? Is that on the other plot?
On this plot.
Yes, right, yeah.
Yeah, so what I'm showing here is the temperature of Na, the temperature when we enter the non-adiabatic era, and the temperature of the axion. And the x-axis is the T reheat. So that would be the temperature here. This x-axis T reheat would be the temperature when the saxions decay. Yep. Yeah, so because you can imagine that if axion is produced here, the amount of dilution depends on the reheat temperature. The lower the reheat temperature means that you have a long era of entropy production, so you have a large dilution. But then what it means is that if the reheat temperature is high, then you don't receive that much entropy production from the saxion decay. So that's why T reheat matters. But T reheat just cannot be too low, so that we don't spoil the heat.
Can you remind me what is it that's excluding this from BDN? Why is it excluded?
Yeah, so that was excluded because if you imagine saxion decaying after Big Bang nucleosynthesis, what happens is that the nuclei will form, but then the decay product of the saxions, for example, Higgs boson or photons, would destroy those nuclei that were formed.
Yes.
So it's very dangerous to decay to produce a lot of relativistic particles after the nuclei form. Yeah. Okay, so we mentioned that this T reheat.
Sorry.
Yeah.
Sorry.
Yeah, no problem.
I just want. I haven't thought about this in a long time. So what about larger reheat temperatures? Why you're stopping in your last plot there? Is there any reason you can't go higher?
Yeah, we could go higher, but the thing is that when you go much higher, then eventually the reheat temperature is actually higher than the axion oscillation temperature, which means that you produce entropy. After that, then you produce axion, which means that axion is not being diluted. So then we go back to the usual story, where you have the axion misalignment mechanism without entropy dilution. And then, yeah, so you'll see in a minute that it is really this region of the T reheat that would help us dilute axion in later plots. Right. So now let's talk about the saxion decays, because we know the T reheat is going to be given by the decay rate because of this condition. So now we have to look at what decay channels we have for the saxion. The first decay channel is this. You can imagine that in the superpotential, we generate a mu term using this kind of interaction. S is the singlet. Sigma, you can imagine it as the adjoint of SU5. So both S and sigma will break PQ, so they get VEPs. And it is the VEP of this term, this operator, that generates the mu term. And we said that S and sigma are charged on the PQ, so the axion, saxion are all in this supermultiplet. So that's why there is a decay channel of saxion decaying to Higgs or the electroweak bosons. So for the X decaying to what they call the visible sector, this is the decay rate. So it is given by the mass of the saxion and also the mu parameter in MSSM and the PQ scale. Q mu is just the PQ charge of this term that generates the mu term. So that's the PQ charge. In most of theories, PQ is just of order 1, either 1, 2, or 3. And D is just the number of relativistic decay products you have. In this case, we have 4 of those, so D would just be 4. Okay, so let's take a look at this plot to see what kind of scale we need to generate the T reheat of our interest, like from a few MeV to 100 MeV. The y-axis is, you can read it as just mu, the mu parameter, and the x-axis is the T reheat. So you can see that for this parameter range, what we need for the mu scale is from a few hundred GeV all the way to 10 TeV, depending on the choice of parameters. So you have to keep in mind that we're doing some TeV or tens of TeV supersymmetry.
I can't read the scale with the colors here. What are the different bands now?
Yeah,
Right
so
after your
this
T?
is Q mu over C
Mhm.
times D
I see.
over 4. And we're choosing it to be 1, 5, or 1, 5, or 1/5. It's just some uncertainty in the parameters depending on which SaxiGUT theory you're looking at. But we expect this parameter to be of order 1. So yeah, so we don't expect it to be outside the 3 bands. Okay, so what are the other decay channels? The other decay channel for saxion is from the Taylor potential, and phi I is the peak breaking fields. As we said that there's the axion supermanipulate, and if you look at the trilinear term, then you will see that there is actually an interaction between saxion and 2 axion from 3 A's. So the decay rate is given by this. This kappa is just defined this way. It's qi qvi squared over vpq squared. And for most of the theories, this is just of order 1 again. Alright, so now let's compare this decay rate to 2 axions with the one we had before, to the center model particles. You can see that it's roughly the same, other than those model-dependent order 1 parameters, except this term, mu to the 4th. So this is the big difference between the 2 decay rates. And in our theory, we have to assume that most of the decays are to the standard model particles, because this is really in the thermal bath. Remember that we want to have the decay of the saxion to generate entropy to dilute axion. So we have to decay to particles in the thermal equilibrium. And here, when S decays to 2 axions, then those axions are relativistic, which means that we're contributing to dark radiation. And I will have a slide of this one later. But you can see that it's very easy that we have this one dominating over this one, because mu over ms ratio is to the power 4. So as long as that's a factor of 2 bigger, then we're completely fine. Alright, so let's look at how we have some experimental predictions. The first one is that we would predict high axion decay constant and low T reheat, as you have already seen. And we will show you how we get the correct axion dark matter. So
Where
first
does the high FA come from again?
Huh?
Why high FA? Where did you?
Yeah, so high FA, yeah, so the picture is this. So initially we're interested in PQ scale and GUT scale to be of the same order.
Right.
And it is because axion misalignment angle, the mechanism that tells us that FA has to be far below the GUT scale. So our goal of the talk or the theory is to have dilution so that we can have higher FA without overproducing dark matter. So this is pretty much the goal of SaxiGUT. We want to put FA back to the GUT scale so that GUT theories
so
and
that's a
PQ
model
theories are...
choice, if you wish. Okay.
Yeah, and yeah, but if you include any entropy, then it is necessarily that you have a higher axion decay constant to produce enough dark matter from the axion. Yeah. Okay. So let's see how we calculate axion misalignment mechanism using saxion dilution. So this is a very short analytic derivation. In the temperature axis, as we said that we want axion to oscillate before reheat temperature. So that after axion is produced, then this is the time when you have entropy production. So how do we calculate this rho A to the S ratio? S is the entropy density, rho A is the axion energy density. And we want to evaluate it at T reheat, because after T reheat there's no more entropy production. So this should be a constant, because both of these are just being diluted by volume expansion. So we expect this to be a constant if there's no more entropy production. That's why we're looking at this expression. So now, how do we calculate it? Entropy we know is given by temperature Q. So TR Q. But rho S, eventually rho S is going to give off its energy. So here I'm doing a Southern approximation. Saxion is going to give off its energy to radiation. So by conservation of energy, we know rho S has to be TR to the 4th. So these two quantities are pretty much the same except a factor of TR. That's how we go from here to here. with the new factor of TR. But now, how do we calculate rho A and rho S at TR? Oh, by the way, there's one caveat. So we want to evaluate this term at TR, but we can evaluate it at the time of axion oscillation, because you imagine that axion and saxion, they are just both energy density of matter, so they should scale the same way, so they should be constant between here and here. The caveat is that, remember that the mass of the axion is not a constant during QCD phase transition. It is actually a power law. So we just have to include a factor to C, which is less than or equal to 1, to correct the fact that the axion mass is changing. But what is still true is that the number density of A and S still scale as constant. It's just due to volume expansion. Yes.
That just kind of bothers me. You don't really mean it's linear, right? You mean it's some power law that goes to 0 and equals infinity. Is
Yeah.
that right?
So this one, sorry, I'm actually drawing it in log scale. So
Okay.
yeah,
Yeah,
log
okay.
scale. So
that's fine.
Yeah. So
I just want to be sure I'm not missing something.
yeah. Yeah, so that is a power law. And then,
Yeah.
so there's something called the dilute instanton gas approximation. They have a power for the power law. It's like 3.4. And then recently, a few months ago, people had the QCD lattice calculation, and they found that this also still follows the power law, but then the new power law is very small, like 1.4 or something. So yeah, so those are the values we're using in the paper that we really use the results people have on the turning on of the mass of axion. Yeah. So anyway, so this C is just a factor to correct the fact that axion is changing in mass. All right. So now how to get to the final expression? So rho A and rho S. Rho A at the temperature of axion oscillation, when it first starts to oscillate, we know it's going to be given by the potential. So it's m squared phi squared. And the way we parameterize phi is that it's just Fa times the misalignment angle. And that's the initial angle you start to oscillate from the true minimum today. And what about rho S? We know rho S can be given by this condition because when this axion starts to oscillate, it starts to oscillate when the oscillation frequency is the same as the Hubble rate. And we know we start to oscillate in the matter-dominated era. So the total energy is dominated by the saxion energy density. So that's why you can solve for rho S in this condition, and that's what you get. And if you have rho A and rho S, then you can plug it back in this formula, and you get the final expression for the axion dark matter abundance. So if you look at this expression, what it really means is that, look at TR. If TR is low, then you have a low abundance. And that makes sense because when you have a low TR, that means you have a long era of entropy production. So that's why you dilute axion more. And it also makes sense that we have a theta squared because when you start oscillating from a bigger initial misalignment angle, which means that you have a bigger potential energy to begin with. So now you can see how we are using TR, low TR, to raise the scale of axion decay constant without fine-tuning theta I. So we can keep theta I of order 1. And then we can get a high Fa from low TR. And this is the number. If you want to get the correct dark matter abundance, let's say if TR is not so far from the BBM bound, then Fa can be pushed up to 10 to the 15 J. Now you may think that, wait, this is not really quite the Gus scale yet. The Gus scale is 10 to the 16. Remember that we want to have the same origin of PQ scale and the axion scale, the Gus scale. So this is not quite there yet. But then remember, what has to be at the Gus scale is not the axion decay constant. It's the PQ scale, the VPQ. And they're related by domain wall number. And in a lot of SaxiGUT theories that we look at, and domain wall ranges from, let's say, 3 to 100. So it's of order 10 to 100. So this puts the PQ scale right at the Gus scale. So this is how we survive the SaxiGUT theories again. So we use the dilution from saxion to push the bound on Fa. And Fa is related to VPQ, and now VPQ is the same order as the GUT theory again. So which means that you can begin with the UV complete theory, where the set of fields that break GUT also break PQ simultaneously. Yes.
So in the models where the for this n is 100, I would guess that that's also sort of the dimension of the gut, some of the gut representations, for example, that are breaking this, right?
Exactly.
So those models are probably pretty unpalatable if you actually try to run them above the gut scale.
Yeah, yeah,
Like they'll have Landau poles immediately.
after the gut scale.
direction.
Exactly.
I mean, is there any model that you think is actually works above the gut scale?
That we didn't look too far into that, but for theories of endomanual of 100, those are the special case. You just have high multiplicity from the multiplets. But we have theories where n is 3 and 5 or 10. So yeah, so I don't think in those theories we will hit lambda pole too early after the gut scale. Yeah, and then and as soon as we get to the gut scale, then gauge unification is done. So yeah, I'm not too worried about what happens after the gut scale.
Consider line C is bigger or smaller than line? Sorry, C.
Kasi?
Right.
No.
Kasi is less than 1. So Kasi inverse is bigger than 1.
What's the total size of
Kasi could actually be 1. So let's look at this plot again. So Kasi is the ratio of the mass of the axion to the mass of axion at T reheat. So it's the early mass to the late mass ratio. But it really depends on where you start oscillating. So if you start oscillating after QCD phase transition, then this factor is just 1. If you start oscillating early, then this ratio is very small because you start with a small mass. And I will show you a full numerical plot to see where this Kasi actually matters. It's actually like the next
So,
slide.
can we get back one?
This one.
No, next. One there. that
Yeah.
one. So you want FA to be of order 10 to the 16 or something, is that right?
We want VPQ to be 10 to the 16. So so there is a common
Now I
confusion.
understand the point. Okay, I got it.
Oh, okay.
Go ahead.
Alright. Yeah, so here's the full numerical plot. Remember we just did a quick derivation to look at the dark matter bonds. But here is the full numerical calculation, including the saxion cosmology, the axion misalignment mechanism, everything is fully numerical. So here I'm showing you FA as a function of T reheat. And those solid red lines are different choice of initial misalignment angle. Let's say of order 1. Then you can see that for high T reheat, then we don't have much dilution from saxion. So we cannot push FA high enough. But then when you have low T reheat, then you can start to push FA larger and larger. And this blue dotted line tells you whether axion starts to oscillate before QCD phase transition or after. This is the Kasi factor. If you're above this dotted line, the Kasi factor is just 1 because you start oscillating after axion mass is already a constant. But below the dotted line, then you have to include the Kasi factor. It's bigger than 1, so that's why there's a deep here. Okay, so what you can read from this plot is that the green band is this. This is the misalignment angle, and the average volume is 1/2. And then if we look at the range between average minus or plus 1 standard deviation, then this is the range, and that's the range I'm plotting here. So what I'm trying to say here is that without fine-tuning, if you just have some random theta, 50% of the probability you would end up being in this green band. So we don't have to fine-tune misalignment angle to push out the bound. Because of the dilution, we're already in the correct ballpark for Fx now.
So the vertical axis is no longer VPQ, though, right?
This one is actually Fa.
Yes, right. So you want VPQ to be 10 to the 16th.
Exactly.
So you would be happy to have FA fairly, an order of magnitude below. Right?
Exactly. So that's why we're happy with 10 to the 15. Yeah. And if you want to connect to VPQ, remember VPQ and FA are related by end-domain wall. So if you have end-domain wall of 10 or 50, then you can see that if for 10, then you expect it to be around this band with some uncertainty in the gut scale. And for 50, then you're here. So what we're trying to show is that for SaxiGUTs, it's consistent that with dilution from saxion, then we have Fa just high enough to have our VPQ at the Gauss scale.
I couldn't see your bands
Yeah.
until Okay.
What's the number on the two upper lines?
This one and this one?
Yeah.
Yeah, those are the misalignment angles.
Yeah.
Of
What's the
pi over 10 and pi over 30.
pi over 10?
Yeah, so it's like 0.3 and 0.1. Yeah, so we really don't need to fine tune the misalignment angles, like 0.3, 0.1. So that's pretty much still very natural. If without dilution, what people have to do if you still want to survive SaxiGUT is that if you want to have such a high Fa, then you have to extremely fine tune your theta. And then yeah, so that's just unnatural. Here with dilution from saxion, then Fa is naturally at the right scale for VPQ to be 10 to the 16, to be at the scale.
So is the standard model Higgs decaying to two axions of any significant rate, or two saxions, or anything of that sort?
Yeah, let me think. I don't think, let me see. Yeah, I actually don't think that we have a decay mode for axion, for Higgs to decay to axions. Because if you look at the superpotential we have,
Right, that's what I was trying to, well, you have that H,
yeah,
H bar S.
yeah,
So if you get H bev, then,
ah,
well, I don't know.
yeah. Probably the decay branching ratio is very small because this term, if you expand it around the minimum, is like mu over Fa. So the branching ratio is extremely small because Fa is large, mu is the quick scale. Yeah, so I don't think we have a branching ratio for the scale of the Higgs. All right, so that's the main result. And it is interesting to point out that in this plot, remember when we did the calculation here, we never need to use the fact that this decaying particle, the matter that's producing entropy, is the saxion. We never really need to use the fact. So what it means is that this plot is actually just a completely general plot. As long as you have some matter-dominated era by some decaying particles, as a function of T reheat, you can find Fa. So this plot is just in general. It's not just for saxion.
But what would happen if you just had more degrees of freedom in the decaying particle, and let's say there was a multiplicity factor of n, there's an n-dimensional multiple. G star was
yeah.
n for that thing, right?
Yeah. Are you talking about the multiplicity in the decay products or the?
No, the actual thing that's decaying.
Oh, yeah. What about that?
Well, wouldn't that increase the reheating effect that would dump more entropy? Because you said it was a general plot, but it seems like you've assumed that there's a single scalar degree of freedom, right?
Yeah, let me think. I don't think we need to assume that because the energy density of the saxion is just given by the conditions when the axion starts to oscillate. So we don't have to assume how many species we have for the scalar particles. Maybe I'm not understanding your
No,
question.
I guess I don't see why it would cancel out, right?
So the idea is that if you have a large multiplicity for the scalar particle, then that would just mean that you will have a higher matter energy density. That translates into the fact that you would have to wait longer until your Hubble is the mass of axion when the axion starts to oscillate. So I think it just changes the axion oscillation temperature, that temperature. Yeah, but I think it's still given by T reheat because entropy is just T reheat cubed. Yeah, so I don't think it depends on the number of species, but the result would be different because of the axion oscillation temperature here. Yeah.
Could you go back to that superpotential for a moment? I just want to see
This one?
the superpotential.
Oh, the superpotential.
H bar.
Ah. Yeah, here. So yeah.
So lambda 1 is of what order here?
So yeah, good question. So S is a singlet and sigma is a 5x5 matrix.
Right.
And because we have to do the triplet doublet splitting, we have to make the triplet Higgs heavy and doublet Higgs of the mu scale.
Mm-hmm.
So we have to do a very high degree of fine tuning here. So this sigma field is 5 by 5, so the depths look like 2, 2, 2, negative 3, negative 3. So we need a fine tuning between the singlet and this one to have the triplet doublet splitting.
Okay. Well, I'm just wondering, coming back to my other question, if the Higgs requires the Bev, then you have a term that mixes the S with the Higgs, right?
Mm-hmm.
So does that, and from what you're saying, that could be substantial.
I don't think it's substantial because after the fine tuning, if you look at the Higgs doublet part, then what we have eventually is just a mu term. That's what we're doing to get a mu term by the fine tuning. And then you will have e to the q mu, the PQ charge of the mu term, times the axion supermultiplet over VPQ, and then h bar h. So when you expand this one, can you see what I'm writing?
Yeah, sort of. Go ahead.
Yeah, so when you expand this term, then what you get is like mu over VPQ to the first order, and then you have the axion supermultiplet, you have h bar h.
Mm-hmm.
So this coupling is extremely suppressed because of mu over
Because
VPQ.
VPQ is picked up, yeah. Where's that exponential coming from? Remind me now.
Yeah, so this one is that, if you look at S and sigma, after they get vectors, for example, some general phi, this phi could be S or sigma,
Mm-hmm.
phi will be expanded this way. So phi q vi e to the qi a over VPQ. The reason I'm doing this is that if you parameterize your field this way, this vi is the value of this field I.
Mm-hmm.
If you do this kind of expansion, then A is really the flat direction in the potential.
I see. Okay, I've forgotten that. All right.
Yeah, so because what we really mean by the axion multiplet is the flat direction in the potential. And then we can only get this correctly if you put it in the exponential. Yeah.
All right.
Yeah, so that's why I think the Higgs decay is not going to be.
Right, but I mean, if you right in what you say, it's obvious. Yeah.
Yeah.
Okay.
Thanks for the questions. Alright, so we saw the main result. We saw how we make SaxiGUTs alive again. So here we're looking at why do we really care about TeV-scale supersymmetry. So here I'm showing you pretty much the same plot. So the y-axis is the dark matter balance. So now I'm not requiring the dark matter balance like this. This one we're requiring the dark matter balance, but here I'm just letting the dark matter balance change. And here the x-axis is just the mu scale. And why do we care about the mu scale? Because remember the mu scale tells you the decay rate of the saxion. And that also tells you the reheat temperature. So I'm pretty much plotting the same thing, except that the x-axis, instead of being T reheat, I'm looking at the mu scale. I'm looking at, if you have a low T reheat, then you have a large dilution to dilute the dark matter balance of axion. And we want to see to what mu we will get the correct observed dark matter balance, which is labeled by this gray band here. So you see that, so there are some different dimensionless parameters that are of order 1, but you see that generally mu is of order hundreds of GeV to a few TeV for us to get the correct dark matter balance. So what we're trying to say here is that it is really the TeV-scale supersymmetry that gives us the correct dark matter balance. And dark radiation. Remember we said that saxion can decay to standard model particles or to axions. We have been assuming that it goes through here. But now we want to see what is the constraint from the dark radiation that would contribute to the N effective observed by CMB. So the way we calculate it is that we just compare the energy density of axion with neutrinos. And neutrino was once in thermal equilibrium, so we look at rho r. And let's remember that rho A and rho r are dominantly produced by the saxion decay. So the ratio of their energy densities is nothing but the ratio of the decay rates. So now we also gave you some formulas about the decay rates to saxions or to the standard model to axions or to the standard model particles. Then we can plug in those formulas, and this is what we get. So this is of order like 0.3, and it is just very interesting that without doing anything, the number comes out to be close to the experimental bound. And here's a plot of the same equation. I'm just plotting this equation here.
See, that capital D in the denominator was
The number of states in the final decay products of this section. Yeah,
okay.
it's 4 because we have these 4 states.
Oh, okay.
Yeah. Yeah. So, yeah, kappa, q, mu, those are of order 1 parameters. Okay, so let's take a look at the result. So here the x-axis is mu, and the y-axis is ms. Why am I plotting these two? Because if you look at the n effective, those are just of order 1, and those we know, so it's really dependent on this ms and mu. And why that matters? Because mu over ms is really the difference between the decay rates to the visible sector and the axion sector. Alright, so if you look at this one, again we have some dimensionless order 1 parameters. So for the green, for the blue one is 0.1, for the orange one is 1 for this choice, and for the theory scale we look at, those are the range. And both the solid thick lines are excluded by Planck because you would just produce too much dark radiation that would contribute to an effective bigger than 0.6. And then the dotted line is the future sensitivity from the CMB stage 4 experiment. So they can probe up to 0.04. That's the region they're probing here. So what is interesting is that if you look at the primary region that we're interested in, mu and ms of order TeV, we're really close to the experimental bound for current and future experiments. So if we start seeing some n effective, that could be one signature of SaxiGUTs. All right, the second to last experimental predictions is the proton decay. Whenever you have a GUT theory, SP5 GUT theory, then proton can decay to, for example, positron and pion with decay rate given by mx. And mx is the X heavy gauge boson. And we know the heavy gauge boson mx is given by the coupling constant of the unification scale, and V5. V5 is also the GUT scale of SU5. And now we know that V5 and VPQ are of the same origin because they're broken simultaneously. But they could be different, so we insert the factor C here. But we expect factor C again to be of order 1. Now if you look at the result, VPQ is related to FA by the domain wall.
Can you just remind me what C is again? Sorry.
Yeah. C is just a dimensionless constant that tells you how different the GUT scale is compared to the PQ scale. We know that they're broken together in the UV complete theory. But for example, the breaking fields, we saw that there's S and sigma. S is singlet, so it doesn't break GUT. But sigma is SQ5, so it's charged under both PQ and GUT. So that's why the GUT scale and PQ scale could be different, because those symmetry breaking fields could be charged on one or the other or both. So that's why these two scales could be different. And we just insert the factor C to tell you that they could be different, but C we expect it to be of order 1. Okay. And now if we look at this result, here I'm plotting again the same thing. Horizontal axis is Q reheat. Instead of plotting FA, like what we did before, I'm translating FA into VPQ, and thus V5, MX, and the proton decay rate. So I'm just converting the y-axis from FA to the proton decay rate. And below around 10 to the 34 is excluded by super K. And again, it is a surprise to us that the parameter range of our interest, like for domain wall of 10 to 40, with this range of T reheat, we're again very close to the experimental bound. So it is possible that in the future we will see some proton decays, and that could be an indication of SaxiGUTs. All right, one last prediction is isocurvature density perturbation. So we know for any scalar field, during inflation has some quantum fluctuation of order hi over 2 pi. And the field volume of axion is given by just the theta times Fa. That's what we mean by the misalignment angle theta. So this delta theta could contribute to the isocurvature perturbation. And this is the current experimental bound. If you look at the choice of the parameters that go in here, this EI is the inflation scale, 10 to 16. And that's the misalignment angle of order 1, domain wall of order 10. And this SI is the initial oscillation amplitude of the saxion, which could be of order plane. Because the field volume gets displaced from the true minimum during inflation, and that can lead us to the cutoff scale. Okay, so if you look at this one, again, we're very close to the experimental bound, depending on these parameters. And this is also very interesting that if by step 2 observe the inflation scale from the demotorization to be 10 to the 16, then we can also get a signature from curvature perturbation. So that's another experimental prediction of SaxiGUTs.
How did we measure this curvature perturbation? Is that called?
You mean CMB? How do
Yeah,
measure?
CMB can really get such a strong limit.
Yeah, let's see. How do we measure curvature perturbation? Yeah, that I don't remember. I will have to look up.
Astrophysicists here, because we don't have them.
Anyone knows how they measure curvature perturbation? Yeah, I don't remember it. Yeah, but that's the bound we take from their paper. Okay, conclusions. So we have shown you that what is very surprising to us is that people kind of overlook this possibility that saxion will actually decay and dilute axion. And it is not like we add the new particles to get the dilution we want. Saxion is always in there if you're talking about SaxiGUTs because it's supersymmetric. So if you introduce axion, you always come with the saxion. So the saxion is always there. So and eventually it has to decay, and the decay would produce entropy, and that is what we need to push the FA back to the VPQ. It's not something that we have to do in addition to the old theories. It's just in the theories itself. It cures itself. All right. The second thing that's surprising to us is that SaxiGUTs would work with axion dark matter if we have the TeV-scale supersymmetry. And the third one is that it is very interesting that SaxiGUTs can lead to so many different experimental predictions. And without much of fine-tuning and so on, we're already close to off the experimental box. So it is possible that we can see any of the signatures in the future. All right, that's all. Thank you very much for your attention.
So it seems that normal SUSY particles are completely disconnected from this story. Is that right?
Yeah, I think so.
You know, this squirts or whatever.
Yeah, I think it's, we don't need to really look at those. But one place it could show up is that saxion, if saxion is heavy enough, then it can decay to other hexenol and other particles. Yeah. But in the current study, we just assume that it decays to these 4 states. But it doesn't really change the story. It only makes this D a factor of 8 if it can decay to heavy Ds.
Other questions?
Did you do well, there's something that depends on the model, right? With all these order 1 factor. Did you look at some more concrete model?
Yeah, good question. Yeah, in our paper, we actually have a section to describe how you actually construct a SaxiGUT model. So we look at quite a few examples. So one example was the one that I showed you. It was the let's see, this one, the Enos and Raby SU5. So this is just how to get the VEF of S and sigma by fine-tuning lambda 1, lambda 2, and lambda 3. You can get a VEF from sigma and S, and this is how we generate the mu term and do the triplet doublet splitting. So that's one example. And there's another example, SO10 by Hall and Raby. And so here, so we do look at quite a few explicit models. And then here's a section about how you just construct one.
Because for proton decay constraint, I usually graph model, the strongest one that comes from dimension 5 operator. But
Yeah.
that's related to how you do double triple splitting.
Exactly. Yeah.
Uh,
Yeah, so the plot I'm showing here is actually not dimension 5.
yeah,
Because,
this
yeah,
is
as you said,
this is gaugeable dimension.
Yeah. As you said, because dimension 5 is just highly model dependent, so
Okay.
to be general, we just look at dimension 6 decay mode. Yeah. But we didn't do any specific model studying for the proton decay for the dimension 5 calculator.
So the usual way write down usually is ruled out, right? You have to do something in order to avoid the constraint.
For the dimension 5
Yeah.
calculator? Oh, really? Okay. I'll look into that. I'll look into that.
Unless you really push the super partner heavy enough, do some split SUSY type, then the minimal model will be fine.
Okay, I see.
Otherwise, usually.
Yeah, that's something that I didn't look at before. I'll look into that.
How does the Higgs mass work?
Yeah, so the Higgs mass is from the mu term. So yeah, so we generate a mu term here. And then after that, it's just the usual MSSM. You have the mu term for the Higgs. And then, yeah, so it's the usual story. After PQ is broken, it's just the usual MSSM story.
For the usual MSSM, you don't have high enough Higgs mass.
You don't have that?
You don't have high enough Higgs mass. And you need loop corrections.
Oh, I see.
Is that the same?
Yeah, I think it's the same for ours.
So it does need to do SUSY or something to make it. Okay, so no other question, let's thank Raymond again.
All right, thank you.